My name is Raia Hadsell. I am the Director of Robotics at DeepMind, and I've been there for about 7 years now. I was actually, I remember giving a Carnegie Mellon seminar talk quite a few years ago when I did a postdoc there briefly with Marshall Hebert. Anyway, happy to be here and tell you about some work that we've been doing for scalable robot learning in complex environments. So let's see here. We all like deep learning these days, and deep learning is powerful because the models readily scale to fit large data sets. We sort of often think about this balance between this very complex model and this very big data. This is well supported by large-scale compute and end-to-end optimization. It all works very well, and success is guaranteed, as some people like to say. And DeepRL, in a way, we can think of in a little bit of a similar way, in that we've got now an agent in an environment. The agent is the learner, and the data set that it is learning is the environment. And that data set is, in fact, created through the interaction of the agent with the environment. So yeah, the model, the agent builds its own data set by taking actions and observing the environment. And this is great because it allows us to couple together actions and observations and rewards in different types of environments, and that allows for optimization over behaviors. And this works in domains such as games and also simulated environments where we even want to have control of a more complex creature like this humanoid figure. And this gives us, has given us a lot of new tools, the sorts of things that DeepMind has worked on and others have worked on over the last decade or so. We end up with new tools to solve old problems and new ones. We also even get to insights in how the brain works. So for quite a while, I was working on a set of navigation problems and wanted to understand how agents could learn to navigate through first-person 3D mazes like this. And we looked at all sorts of different methods from approaches like Merlin that couples together a neural memory with a sequential VAE and trains the entire thing end-to-end using reinforcement learning, work on looking at what are the representations within the agent when you learn these sorts of environments and whether or not they are similar to that of biological brains. But it's time to move beyond this simple picture. It is a cartoon after all. And I think that the results, while incredibly powerful, also start to fall a little bit short when we look at more important, especially important real-world problems. And I think that perhaps the problem here lies with this idea of that our agent needs to somehow be similar to the environment, that the agent can fit the environment, that in order to learn to be superhuman at Atari, then that agent needs to be complex enough that it can learn in some ways everything that there is to know about Atari. And that's just not how the real world works. The real world is much more complex and has so much rich complexity to it that we would never think about memorizing and learning deeply the entire thing. So a claim that I would make is that agents need to be smaller than the environments that they learn. And what do I mean by that? Well, I mean that agents are smaller than environments when the size, complexity, and richness of the environment far exceeds the capacity of the agent to model them, or perhaps the agent does have a lot of capacity, but the bottleneck of observation and action between the agent and the environment, that is constrained enough. So the human brain is very powerful and very, very high capacity, number of molecules in the universe or some such. But the outside world is extremely complex as well. And there's this bottleneck here that I can only experience things sequentially through time using limited sensory capacity. And those limitations are important in a way that defines who we are as humans, the fact that we cannot see everything, we cannot know everything all the time. So we learn to live with the limitations of not seeing everything at the same time, not being able to look in all directions at the same time, and that gives us some of our cognitive capabilities. So having this bottleneck is the driver of all sorts of wonderful things. Of transfer, we have to learn to transfer well because we don't have time to relearn every new thing that we come across, right? So we need to learn to be good at transfer and at generalization as well. We have to be good at fast adaptation. Again, there's only so much time that we have, and we have to be able to react to new things because we can't just learn everything. We can't fit the world like a big neural network fits an ImageNet data set. We can't do that. We have to learn to generalize. We have to learn to adapt quickly. We have to learn to continually learn, right? Because we have a sequential experience of the world, then we need to be able to accumulate our information over time, to not forget, to build representations and build knowledge over time. Causal reasoning as well is a way to handle the fact that we cannot see everything, that we cannot experience everything, and abstract concepts as well. So we want all of these things. I would argue that the first step is to think about machine learning problems in domains that have this quality where there's a severe bottleneck or where the agent is much smaller than the environment. So how do we make an environment complex? Well, a few different things come to mind. First, when we think about observations, real data usually has more complexity to it, often just because it has more noise, but also because there's a lot of underlying causal factors. There's partial observability, sorry. Like I said, a limited bandwidth on our observational space. Multiple sensory modalities. So multiple sensory modalities allows an environment to be more complex because we're getting information through multiple different modalities, multiple different senses. Dynamics. So we can think about the dynamics of interactions and contacts with the world. This immediately is going to impart more complexity because of the nature of contacts and interactions, and the fact that change happens when there are interactions. Multiple agents, of course, is very important. And then we can think about the qualities of the world. So instead of environments that are fixed in time, we can think about persistence and different expanses of time, things that happen over short time scales, medium time scales, long time scales in a persistent world. All right, that's how you might make an environment for learning more complex. This is how we might think about if we wanted to build an AGI by learning in an environment. Well, I would argue that we would need to have this amount of complexity in a simulator, or we would need to be able to learn directly in a real world environment. How can an agent learn if we've posited this complex environment and a limited bandwidth constrained observation space and action space. And so there are a few different things here that I think are important directions if we want to be able to solve this type of problem. The first is learning over different timescales. So there's been a lot of focus recently on learning over very short timescales, such as solving these Raven's progressive matrices, or looking at biologically how ravens learn, can adapt very quickly, or learn new puzzles, learn new problems, and methods like mammal and meta learning really focus on that question of how can we learn to learn quickly, like humans do. But you know, that's not the only hallmark of intelligence. That's one that we tend to look at, but it's not the only one. So learning over short time scales is important. And also look at learning over very long time scales, right? A cheetah becomes very good at what it does because you can think of evolution as being a very long training regime over a very long time of optimizing over a lot of experience in almost the same way that this humanoid is also optimized to do only to maximize forward velocity. So we have methods that will train short time scales, long time scales. I don't see methods that put this together. I don't see methods that can both learn slow and learn fast, and do this well. All right, so another way in which agents could learn better is by learning with multiple objectives. So many RL objectives, for instance, or combining the whole cake here, as we like to say, and putting together both the RL cherry on the top with the supervised learning and the unsupervised learning. And I'll talk a little bit more about this type of approach later in the talk. There's learning with many tasks or skills. So this is a way to encourage the learning of transfer, shared features, abstract concepts, because it's only through learning over many different skills that we really see the requirement of learning transferable features, transferable skills, behaviors, etc. And for abstract concepts to start to emerge. So in the space of a complex environment, it should also have a large number of different skills which can be learned by an agent. And this will allow us to, I think, do a better job of learning transfer concepts, etc. And the last thing I would highlight is learning with humans. So being able to learn from demonstrations, through imitation, through simple observing, and through language. These have all, of course, been studied in machine learning, HRI field at CMU and elsewhere for a long time now. But you know, but this is quite important. This is an aspect of multi-agent in complex environments. And there are so many different ways in which we can learn through interaction with humans, or even simply from observing humans. Sometimes I'm struck when I am in a crowd, which has not happened in a very long time, but when I used to be in a crowd, for instance, commuting on the tube in London, then I was struck by how much I learned from simply watching what other people did, rather than through any need for active imitation. And this is supported by things like motor mirror neurons in the human brain. All right, so that's sort of just a painting a little bit of a perspective, a little bit of a position of where I like to be in terms of doing research, leading research at DeepMind, and thinking about some of these problems. Now I'm going to talk about two specific research projects that we've been working on over the last year or so. And there are not many real robots harmed in in this research, unfortunately, because our lab has been closed for most of the last year, a couple windows of access. So I'm going to talk about representation learning and imitation learning. So representation learning, there's two different ways in which we can think about this from the perspective of robots. Well, there's probably more, but I'm going to highlight two ways to think about representation learning. The first is representation learning for the point of having better features, which are rich, which are multimodal, and which will support a lot of downstream learning that we would want to do. We do representation learning so that we can then use that representation to take actions, to learn a task, to do something else. And so we might want that those features are better, are rich and multimodal. On the flip side, we might want to do representation learning so that we can learn features that are invariant, where we're actually throwing away some of the richness because we don't actually want to have things like shadows and textures when we're doing, in this case, manipulation tasks for a robot. So two different sides of representation learning, and then two different sides of imitation learning. One is you can use imitation learning as a way to take advantage of a lot of data in order to learn a set of skills. So this is looking at a lot of behaviors done by people and saying, how can I learn those and make those be a base of skills so that I can then reuse them? The second way to learn to use imitation learning is say, actually, I'm going to start with a model representation, and I'm going to use imitation as a way of demonstrating novel tasks, as a way of very quickly getting from a base architecture to a set of new tasks that I would want to execute on. And so the two sides of imitation learning, two sides of representation learning, hopefully will come out a little bit. All right, so first of all, we've been looking at representation learning for tactile robots for quite a while. And this is work with people on my team, in particular Martina Zambelli. And this highlights the first one, representation learning for rich multimodal features. So touch is important, underappreciated perhaps because it is hard to have on a robot. There are tactile sensors out there, but there's nothing that's really accepted and standard and produced by industry. But you know, touch is quite important. Often vision is not available to solve a task, and of course we might want to we want to be able to identify objects and have a certain amount of precision of control with objects even when we can't see them. Humans rely on having a mental model of the target object available, but also not. We can form that mental model purely through touch, and definitely underutilized in robotics. So in robot manipulation, then we have in particular the problem of occlusions, limited vision. As soon as you want to reach in and engage with a set of objects or a task, you're going to run into that problem of that as soon as I touch the thing, the block, the screw, the tool, whatever it is, now you've occluded it. You either have to have very good active vision in order to be able to still have a good view on that object, or you need to be able to recognize it and manipulate it through touch alone. And from this point of view, we would like to explore cross-modal representations of objects. And we think that this is pretty fundamental for robot manipulation. So in this talk, I will outline a pre-training process that involves using proprioception and touch and vision to learn a set of features. And we have data from a simulated shadow hand, which has 5 tactile sensors, and we interact with different sets of objects. And so we use purely self-supervision and cross-modal losses, so without any explicit supervision. So not trying to identify the objects, but simply trying to align and learn between the different sensory modalities of vision, touch, and perfume. And then we evaluate the touch features on different sorts of tasks, for instance, few-shot object recognition and pose classification. And of course, in a real system, then we might want to fine-tune the entire pipeline. We might want to train it all together. But in this case, we wanted to get at what are the loss functions, architectures, and approaches that will lead us to having a better set of features, better representation. In order to build a data set, we started working on this, and about a month later, the lab was shut down because of COVID. And so we really didn't have any other options other than to turn to simulation. Luckily, we have a good model of the shadow hand and different sets of simulated objects. And instead of trying to, for instance, teleoperate the shadow hand, which is challenging, instead we simply trained a policy, used max a posteriori policy optimization, or MPO, in order to train an agent to touch different objects. So fixed wrist, and the agent is given a reward for having fingertips in contact with the object. You can see the fingertips turning yellow when they contact. And this was the basic architecture that was used, with a few variations. So vision is collected, fed through a convnet, producing camera features. And then touch is combined with proprioception, fed through a feed-forward neural network, and then through an LSTM to produce touch features. The LSTM is important because you need to be able to integrate data over time, because we get these sparse activations, sparse observations from the tactile. Then we can put together these two different feature spaces using different methods for cross-modal self-supervision. We can decode from this feature space and try to predict directly the images. So this gives us cross-modal generation loss. And then we can take whatever we end up with for our touch features, take away the vision side of the architecture altogether, so that we only have the tactile, and see how well we do on a downstream task, on an evaluation task. This steps through it. I forgot that I'd done this. So yes, we've got the camera features, we've got the touch and the proprioception through the MLP and LSTM. And then we've got training these touch features. And there's a few different methods there, which I will mention more in a moment. So one method is L3net. This was published by folks at DeepMind a couple of years ago. This does binary classification of synced and non-synced pairs. And so this was adapted for use in this case with touch instead of audio to pair up with the vision. It's a binary cross-entropy loss. And then there is CMDC, which is cross-modal distance classification, which predicts the temporal distance between a given pair. So it tries to look at different pairs and predict how far away they are in time or how close. That's trained using a softmax cross-entropy loss. Other than that, it is quite similar to the L3net. We have time-contrastive networks, which are published by Pierre Sermonet and others, and CMC, which is contrastive multi-view coding. Both of these use a contrastive loss in order to look for higher similarity between synced pairs on different camera views, in this case, vision and touch. And then CPC is contrastive predictive coding. It predicts the future latent observations using current latent observation in the previous context. So that's what this looks like. Take a sequence of observations in, and then from a latent space, then predict n steps into the future in the vision modality using a trained encoder and decoder. And then lastly, we have cross-modal generation, which directly generates one modality from the other, in this case, vision from touch. So in this case, we are directly training a decoder. And note that here, the loss function means that we are actually backpropping vision information through to the touch features. So there's a bit of contamination there in that generative process, in that training process. All right. I know I'm going quickly. Hopefully, it's not too much. I know that you CMU's folks are sophisticated researchers and probably know all of this already. So I'm just going to charge on quickly, but feel free to jump in if you have questions. So like I said, we're going to try out evaluate all of these different methods by then finding out which ones have trained good touch features so that we can then learn to discriminate different objects or different poses of the hand. And the way in which we tested this, of course, if we can use lots and lots of samples, then all of the methods are probably going to work well because of the magic of training whatever you want into a nonlinear network. But if you do few-shot learning, then you're able to see really how good those features are at training for the downstream task. So those are, so the rows here are all of the different approaches to train the features, the representation. And then the columns are how many different shots, so how many different examples we looked at. And then we also looked at learning from raw features alone. In the sets of results, we are training on one set of object, or the training on the objects is the same set as we're testing on. So we're not changing the objects at all. We're just changing the data that is used and the task. Initially, we're just trying to learn good features. There's no supervision, and then we're using supervision to actually identify what the object is. And we can also try this on a different set of objects. So we have either a set of different geometric solids, different sizes and shapes, or we have the YCB set of objects. And so if we look at these results, what we can see is that the CM-Gen method, which is the one that generates, directly predicts the images from the touch features, does quite well and does significantly better than training from scratch. However, if we look at cross data set experiments, where now we are training the representation using the set of geometric props, and then we are transferring it and trying to learn to recognize the YCB objects, or the reverse, then what we see in both cases is that with enough shots, then all of the contrastive methods do about the same, but we do significantly worse if we try to learn from scratch, and we do significantly worse if we are using the generative features. And this is simply because the generative method has overfit badly to the training set that was used because of the problem that the visual feature information transfers into the touch information a little bit too deeply. We can look at another problem. This is few-shot pose estimation on the YCB objects. So this looks at the different methods and now says using the same sets of features that have been trained, let's learn to predict the pose of the object from a limited number of trajectories for training. And what we see here is that the performance of that generative method, of the cross-modal generative method, falls off dramatically because it has not learned perhaps the appropriate features from vision, and they are certainly not robust enough. The contrastive methods all perform significantly better. All right, so that's it for this method. We really just wanted to do a careful examination of different methods for comparing across different feature sets. And self-supervision is a natural and effective way to learn between different modalities, such as touch. And overfitting is a risk in this, which I think makes a lot of sense. But we see it in general that the contrastive methods can all work well for this type of problem. And those data sets are available. We've made them all open source. The next piece of research that I wanted to discuss is called COMIC. This is an acronym for Complementary Task Learning and Mimicry for Reusable Skills. And the lead author on this is Leonard Hassenklever. And this is to look at that first use of imitation learning for learning reusable skills. So imitation learning that takes advantage of lots and lots of demonstrations of different behavior in the world, using that to distill a set of skills that can then be used for downstream tasks again. So why do we want to use reusable skills? Well, learning is from scratch is certainly possible. It requires a lot of good task design if you want to get a really robust behavior out of it. It can be pretty darn data inefficient. Our methods here have gotten better since this original parkour paper from Nicholas Heese. But this still takes quite a long time to train and to train well over these different types of parkour terrains. So what we would like instead is to learn reusable skills. So explicitly learn skills which can then be reused for downstream tasks to give us better data efficiency, robust performance, and better exploration efficiency. So there's different types of methods here. Unsupervised skill discovery methods, lots of simple tasks, decomposing a more difficult task into lots of simple ones. Or demonstrations, or specifically training different types of tasks. So what we propose here is starting with motion capture tracking. Sorry. So taking a sequence of use that. No, right. Taking a sequence of frames and encoding them into a latent space Z, as they say in the UK. So encoding a state into a latent space Z, and then training a low-level policy conditioned on the target state information that's going to produce an appropriate action in order to track a sequence of frames. And then this can be reused by taking only the latent embedding Z and training a new high-level policy that makes use of it. So now we're going to freeze everything here that's downstream. It's similar to, in concept, to using the feature learning that I showed in the last section of the talk. Using that, But here we're freezing a low-level policy that is conditioned on a particular state and produces actions. And we're going to relearn the high-level policy so that we can control this new action space. So rather than directly generating actions, I'm now controlling what information I feed into this latent embedding space. Now, this has been used in a number of recent works over the last couple of years. So it should be relatively familiar. And sorry. What we can also do, however, is instead of having that decoupled architecture, we can consider a shared embedding space where we are training that same embedding space for both the encoder and low-level policy, and at the same time for that high-level policy that's coming from a task. This allows us to combine two different sorts of training. One is doing imitation directly, tracking a set of data clips, and at the same time trying to maximize reward for a different type of task in the environment. These two different objectives can be put together, sharing part of the same architecture, just like we might have a shared visual feature space and train it at the same time for a detection, a tracking, and a classification problem for computer vision. So the research questions to be asked after getting this working is what is the influence of different types of architectures, different types of model components, and how do these work in terms of tracking performance and reusability? And how well does the joint training approach work?
Ray, can I ask a question?
Sure. Hi, Dave.
Sure. Hi. Sorry, I'm not sure if I fully understood. Is Z supposed to capture the task, or can you explain that one more time?
Yeah, so Z is going to be a latent space that is going to capture all of the different types of distinct behaviors that are required to either imitate the motion capture data that we use, or to generate high rewards or returns from the rewarded task that we might be training at the same time. Now there's different, we just treat this as being a multidimensional latent space without any restrictions put on it, just regularized. But there's also, one could look at this as being a space in which clustering could be used in order to separate more explicitly some of the different skills that are learned. But essentially that shared embedding space is going to encode within it the different types of skills that make up the problems here. And then it can learn to be controlled as well. It can learn to be produce any type of low-level policy that is within that training data.
That makes sense. Yeah. Thanks.
So the data that was used here was the CMU motion capture data in a humanoid model with 56 degrees of freedom. And in each episode, we sample a starting point from a large number of different clips. And we use a reward which has terms for each of the individual joints, absolute positions, and joint orientations. So this is just learning that tracking task. So this is done using large-scale on-policy RL training using VMPO. So in order to match those tracking, in order to track those different trajectories, and with KL regularization of the embedding space of Z space to a standard normal distribution. And then we looked at different types of low-level architectures. So what is the component that's used to implement the low-level policy? It could be an MLP, LSTM, mixture of Gaussians or product of Gaussians architecture. Then we used 4 different motion capture data sets to look at how well different types of data produced different skills and how easily they could be learned. So the smallest here is only a 2-minute long data set, and the largest is 3.5 hours. So quite a big difference here between these different ones. And then in order to look at the transfer, to actually evaluate this for transfer, then we looked at a go-to task, where there's a new point, a new location given on each episode, and the agent needs to get there as quickly as possible. And then 2 different parkour tasks where the agent has to navigate different sizes of gaps and also run between obstacles, wall obstacles. And so these tasks have a dense reward, and they use egocentric visual observation. So it's actually first-person vision that's used, as well as the proprioception of the joint positions and velocities. And then to understand how well the joint training works, as has been proposed in this paper, then we looked at additional tasks that require skills that are not covered by the motion capture data. So for instance, getting up from the ground is not covered in any of those data sets, and also catching a ball is not covered in any of those data sets, which has no objects in them. So the tracking performance, the question of how well can the different types of architectures, different types of models actually fit that data of anything from the 2-minute walking data set to the 220-minute large data set. And in all of these, we see roughly a similar performance, which is that the LSTM does the best at fitting this tracking data, the mocap data. The MLP does next best. And then the product of Gaussians and the mixture of Gaussians do not work as well on any of the data sets, large or small. And here's a little clip of the tracking performance. So this works almost very well. So this is the agent, the gray figure there is what's being tracked. That's the motion capture data set. And then the gold figure is trying to match the entire trajectory. And you can see that it doesn't always quite do it. It skips things that are occasionally a little bit too challenging, perhaps, and then gets back in sync with the clip as quickly as possible. But it works quite well. Having a different combining rewards that are placed on every single joint is quite valuable here in making sure that we're really learning about the fine scale of imitating the hand motions and all of the aspects of the demonstration. And so in this case, however, when we look at the downstream tasks, then what we actually see is that the MLP performs the best across the board. So the LSTM has essentially, even though it did very well at tracking the mocap clips, and learning to do that, it now is suffering at learning the go-to-target test, and the MLP does significantly better in almost all of the cases. So similarly to the previous section on the cross-generative model versus the contrastive methods, then here we see that the slightly simpler architecture of the MLP is less prone to overfitting on on the initial task. And then this is an agent that has been trained on the GATS task after being initially trained on the large mocap set, or actually is trained jointly at the same time.
Hey, Raia, I have a question. So since you're jointly training two tasks, what is the assumption of the relationship between those two tasks? Is it like if you're learning a mocap of walking, then the task it is being trained on is just walking on different terrains? Or like during training, how would these two tasks affect each other?
Yeah, we looked specifically, we were trying to find things that were only connected by the body itself, by the model itself. But other than that, required different strategies. So if we used a similar problem, for instance, the closest one was just the go to target task, because that used the walking sort of general gait control that was in the mocap. Even there, it took a significant amount of additional training to, or a significant amount of the balance of the training. You can sort of split up the gradients and weigh them both between the two objectives. It took a significant amount to learn that. And then we saw that it was more challenging as you start to pull these, make them significantly different, like getting up from lying down, catching a ball, these sorts of things. But really, I think this is just about the capacity of the latent embedding space, and it does work to train on quite different tasks. The challenge, I think, is that when you train using RL for the rewarded task versus RL for the imitation task, then the dynamics, the learning dynamics can be quite different. And so exploration is learned at different times, and there can definitely be some interference there between the learning. So it is slower to do this than it would be to train on them individually. But you get this added advantage of having a robust behavior, and it helps on exploration for some tasks that otherwise would be very hard to train on.
Okay. Initially, I was thinking if you learn with the mocap dataset to, for example, stand up, how would that be used to walk better or to run better? But later, now I'm thinking, even you learn to stand up using the mocap dataset, you don't have to use that embedding. So it won't like affect the training of the policy, even you are learning a different skill from the mocap dataset.
One of the questions is how do you keep that embedding space from becoming quite degenerate and quite decoupled from different things that you're learning? So there's nothing to really force it other than regularization to not learn quite different things for the online rewarded task versus the mocap tracking. I think that that's an interesting question. My guess is that this would be something that would go away in the scale of large number of tasks. Then you would need to learn a really nice, compact embedding space to solve all of the problems, to solve all of those tasks.
Okay. Thank you.
Okay, so that's actually the end of that section. I will say that the result here, if you're familiar with the parkour results that I showed at the beginning, there's a certain amount of exuberance here to this agent that is trained to only do these tasks that you lose when you regularize against the human mocap data. We have lost the exuberant flailing arms because the because the learning process is a little bit better regularized by starting with that motion capture tracking, and also because then now the space is a little bit more constrained. And this approach may never be quite as optimal as that initial one is. Going back a little bit to the cheetah versus other types of learning approaches. All right, I am just about out of time. I wonder, and actually this work is something that we just finished and has just been put onto archive, but I don't even have a link for it yet because it was still being processed on archive. Maybe I will just save this for people to find on their own when it comes out. I can give a very high level view of it, which is that, what is the best high level view of this? The high level view of this is that we're going to learn a representation which is constructed using aligned trajectories from simulation, which some use domain randomization, some use randomization of just the arm or different arm types, and some actually have the arm being invisible. So it's relatively easy to take trajectories to apply different types of randomization. And then what we do, however, is to learn a representation that is invariant and smooth. So a manipulator independent or agnostic representation which uses temporal smooth contrastive networks and goal-conditioned, trains a goal-conditioned policy. What this means is that we can, from a third-person view of a human hand moving blocks around in this space, then we have a policy that can imitate that. So it's goal-conditioned. It will try to imitate waypoints on the trajectory that's given. And it allows us to track a real robot demonstration that's captured from a real video, track a pickup stick demonstration here in the middle on the top that's used, or track a representation using a different robot hand. And these are invariant to different viewpoints and to different arms and to different tasks. So we're purely giving reward on the basis of matching the goals that are given using the demonstration rather than any actual task-specific rewards. So the data here is from a stacking task of different types of blocks stacked on top of each other. But the agent is simply trained to track trajectories using coarse waypoints along the ways. And like I said, you can read the whole paper. It should be out later this week. And the name of it is Manipulator Independent Representation Learning for Visual Imitation from Yuxing Zhu. All right, those are a bit quick. Those are the three papers that I wanted to talk about with you today, and happy to take any more questions.
Claps. Is there any question from the audience?
And I had a quick question. This is Greg Shannon. That the plank, the jumping between planks, and the losing that flailing of arms. When you mix the modalities of the terrain, if you were to alternate, say, between two types of terrains instead of just the planks, you know, would you expect the arm flailing model to really be outperformed by the more regularized model?
The arm flailing model is very robust across a wide range of different types of tasks. different types of terrains that we've generated. That works extremely well to get, it's trained for forward velocity. That's what it does. It's going to outperform the one that is constrained by this latent space. The one that's constrained by the latent space that's been learned from the mocap is never going to be able to learn a new strategy of flailing its arms. Or at least it's unlikely to find that because it's not there in that latent embedding. So I think that we lose a little bit of expressiveness in the model, but what we gain is skills that can be quite quickly reused for new types of challenges.
Excellent, thank you.
Dave, you also have a question?
Sure, yeah. So yeah, really nice talk. I guess you pointed out the similarity between the first two projects, that there's an architecture that performs well on the training task, but doesn't generalize as well to novel tasks. Are there any kind of general insights you picked up of how do we design methods that can transfer well? Like how might we predict in advance whether something might transfer well to new tasks?
I mean, I think that to some extent, transfer is, I prefer to focus on, there's the question of generalization, there's the question of fast adaptation. And I think that generalization is always going to be very hard, or transfer, zero-shot transfer. Because I think that to some extent that's the wrong thing to go after. Instead, sort of the very fast adaptation should be something that we're working on, and that really implies that you need to have already learned the appropriate skills, features, etc. The question is, how can you be very flexible if you're given a very short window of adaptation, which I know is something that meta-learning has focused on as well, and that architectures like GPT-3 do well as well. In terms of general rules, I think that a lot of data, a lot of experience, and good regularization are important. But yeah, I don't have any principles here.
Yep, great, thanks.
I also had a question if we have time for one more. Thanks for the talk. I thought the manipulator independent representation learning idea was pretty interesting. I had a quick question about, so you mentioned it uses aligned trajectories. By aligned, do you mean just temporally aligned, or do you also have knowledge that two different trajectories across some variation are performing the same task or executing like the same overall sequence of behaviors?
Yeah, we generate the different trajectories are as aligned or unaligned as we want them to be. It's simply saying that in simulation, we can take a raw trajectory that we have as a sequence of states, and we can apply all sorts of different points of view. We can we can add noise to exactly how those states play out, and we can add different visualizations. This has been used a lot for robust sim to real, for example. This is used at the same time as learning the goal condition policy, gives us a really nice way of getting to manipulator invariant imitation of policies. So we're deliberately adding these different types of trajectories, but they are aligned already because it's in simulation. Hopefully that answered the question.
Yep, thanks.
Any other questions?
All right.
All right. Yeah. Okay. Well, let's thank Raia again for this amazing talk. Yeah, clap. Click the clap. It's a little bit
I
weird.
can
Yeah.
imagine the clapping. It's all right.
Yeah, it's usually, yeah.
It's one of the things I miss most about real talks is
Right.
actual
Correct.
claps. All right, great. Thank you very much for having
Well,
me.
yeah, thank you, Raia, for attending, and thank you everyone for attending the seminar today.
All right, thanks.
Stay
Goodbye.
safe. Take care.
Thanks.